Okay, let's start today's lecture. First of all, I would like to say that starting from today, on the next part on seminar, we will have some problems, list problems, I mean. If you are here, then of course I give you a list. But if you are not here today, then just everybody can write me on this email, and I will send I will send the list. And also actually it is desirable that every of you write me just a letter that you want to attend the course. The matter is that sometimes there is some information, maybe, and so on, and I will send it to the list of those who have written me. Okay, so let's proceed. Last time we start discussing de Rham cohomology of a smooth manifold, and to start for today, I want to be more careful about homotopy axiom. An important theorem, and a very easy theorem, is that homotopy maps, well, pullbacks in de Rham cohomology along homotopy maps coincide. Along homotopic maps so if you have a map and you have two homotopic maps to a manifold, another manifold, and you have two homotopic maps, then pullbacks in de Rham cohomology coincide to each other. This is just an easy consequence of the fact which we discussed last time. The fact which we discussed last time is that if we have a manifold times a real line, and you have just this manifold, then there is the projection and the zero section, and the corresponding maps in complexes of forms are homotopically inverse to each other, and the corresponding maps in de Rham cohomology are just inverse to each other. We have discussed it last time, and how this can be applied to that theorem just immediately. Actually, what is a homotopy? A homotopy is a map from M times a segment to N, but in all this stuff concerning de Rham cohomology, we prefer, at least at the moment, we prefer to work with manifolds without boundary, and this is a manifold with boundary. But it is not a difficulty. The matter is that we can always, first of all, homotopy is a continuous map, but a continuous map can be always approximated by a smooth map. This is a general assertion, and moreover it can be approximated by smooth map which is identical on some collars of the cylinder. So we can say that our homotopy first stay our manifold, first our map doesn't change, then it begins to change, and then in the it is also constant near the end, and then you can immediately extend this map to M over R. So speaking of homotopy, you can always think about smooth map from M to R to N, so that restricted to M to 0 and to M to 1, we obtain those two maps F0 and F1. Now, we can consider here two embeddings, 0 section and section to M to 1. And these two composite maps are just F0 and F1. And since we know that both S0 and S1 in de Rham cohomology, both of them are inverse to P star. So they coincide. So S0 and S1 induce the same pullbacks in de Rham cohomology, hence F0 and F1 induce the same pullback. So this is very easy and very standard explanation, and nevertheless this is a very important theorem. And of course, in a standard way, this theorem implies that de Rham cohomology is homotopy invariant. So if we have two manifolds and we have now homotopy equivalence between them. What is a homotopy equivalence? We have two maps which are homotopically inverse to each other, so that their compositions are homotopic to the identity. Then, of course, we immediately obtain that F star and G star are inverse in de Rham cohomology. Well, this is standard corollary of that theorem, and we have this homotopy invariance, and of course we will use it very often. Okay, next step. Well, next again rather easy thing, but I would like to mention it, is that I have already told it last time, but I would like to repeat briefly that forms on some manifold, this is not only forms of each degree is a vector space, but altogether this is a graded commutative ring. Graded commutative means that it is differential satisfies Leibniz rule. And a consequence of this is that product of two closed forms is again a closed form, and product of a closed form and an exact form is an exact form, and as a consequence de Rham cohomology is also a graded commutative ring. What is important here and what is actually interesting here is that we have commutativity not only on the level of cohomology. In any cohomology theory, you can consider, say, singular cohomology, you have commutative multiplication in cohomology. But usually you do not have commutative multiplication on the level of chains. This is a big problem that when you deal with, say, singular cohomology, you cannot make multiplication on the level of chains. You have standard Alexander-Whitney formula for multiplication of cochains, but you cannot make this multiplication on cochains commutative. In fact, you can. And the history is that actually multiplication in cohomology was introduced by Alexander and Kolmogorov in 1937, and originally in Kolmogorov's approach, the multiplication on the cochains was commutative, but it was not associative. So, of course, if you have any multiplication, you can always turn it to a commutative one, almost just by, if you are allowed to divide by 1, you can always consider something like that, sign depending on degrees. But then it is not associative. It turns out that associativity is more important than commutativity. So everybody prefers to use associative but not commutative multiplication. But here in de Rham theory, it is a rather important and nice fact that we have commutativity on the level of cochains. And actually this has important consequences. Maybe I will say it later, that from here there is a way suggested by Sullivan to make commutative models for singular homology as well. But okay, I will say of rational singular homology. But okay, I will say it later. But at the moment we have this fact that it is graded commutative on the level of forms. Okay, let us proceed. And last time, another important, when you build usual cohomology theory, there is some set of axioms, Stirner-Ellenberg axioms. We cannot have here the full these axioms in full generality. The matter is that we prefer to work only with manifolds. It is hard to even to formulate these axioms only for manifolds. In fact, I would like to say that we could proceed as follows. We could say, okay, we now have homotopy invariance, so we can define cohomology of any, say, finite CW complex as in the following way. We take CW complex, we embed it in some large Euclidean space. You take a regular neighborhood, which is an open manifold, and we say that by definition cohomology of this complex is cohomology of that neighborhood, or we choose neighborhood so that our complex is the deformation retractor of it. And since we have homotopy invariance, this is well defined, independent of the neighborhood, and actually we can prove that all axioms holds, but I prefer not to do it. We never need it. But at least some of the axioms we have homotopy invariance. And an important thing that we have an analog of exact pair, non-exact sequence of a pair. We do not have a non-exact sequence of a pair, since we prefer not to work with pairs of manifolds at all. But a good analog, an equivalent thing is Meyer-Vittoris. Meyer-Vittoris sequence, and last time we have proved this non-exact sequence. Okay, this is some remind, just I recall some things, but now let us go further. Further, we will need another important variant of de Rham cohomology. We will need de Rham cohomology with compact support. De Rham cohomology with compact supports. What is this? First of all, what is a support of a differential form? If we have a differential form on a manifold, then by definition the support of this form is the closure of those points where omega is non-zero. So, and at each point we can take, for each point in M, we can take just omega p is this form in, it is just an element of kth exterior power of contingent space of M at this point, so it is just finite dimensional space. And we can take the closure of all points P such that omega P is non-zero. This is a standard definition, and well, we can consider only those, allow only those forms which have compact supports. So we can consider this C is for this compact support. Omega K of M is the set of all forms in omega K of M such that support of omega is compact. Of course, if the support is always a closed subset just by definition, and of course if the manifold M itself is compact, then the support of every form is compact. So if M is compact, then there is just no difference between compactly supported forms and all forms. Any form is compactly supported. But if M is non-compact, then there is a difference, of course. And well, what is it is obviously that if a form has compact support, then the differential of this form again has the same compact support, maybe smaller but not larger. So of course this is a cochain complex. Cochain complex. And we can consider the corresponding cohomology. As usual, the kernel of the next map by the image of the previous map. So the RAM cohomology with compact supports is by definition the cohomology of the cochain complex of compactly supported forms. Okay, just to see the difference between usual de Rham cohomology and compactly supported de Rham cohomology, let us consider example. Let us consider just a line. What is the usual de Rham cohomology of a line? Of course, we have R in 0, yes. This is R, and this is 0. And all others are certainly 0, since we just have no forms. What concerns compactly supported cohomology? What is the 0th compactly supported cohomology of R? This is of course 0. The matter is, what is a 0 form? 0 form is just a smooth function. We would like to have those smooth functions which have differential 0, so this is constant smooth functions, but we would like this function to have compact support, of course, hence it must be 0. And what is the first de Rham cohomology? Yes, this is R. Well, first of all, we can consider a map from here to, from the first de Rham cohomology to R. The matter is that if we have a one form with compact support, it is of course always closed. All one forms are closed on R. But then we can integrate it over R. Though R is not compact, this integral is well defined since the form has compact support, and in fact we integrate over a compact segment. So this is a well-defined homomorphism. It is. It obviously have. Obviously it is surjective. Why? It is surjective because okay, if you can just consider such function with integral. This is 0 s and with integral 1, and you can take the form e, which is, let this function be h, just h of x dx. Then this form integrates to 1. So this is surjective homomorphism, and also it is injective. The matter is that if form integrates to 0, then we can consider a function. What is a function? Function f of x is integral from minus infinity to x of omega. And okay, this function, first of all, df is omega, then this function is 0 at minus infinity, then it behaves somewhere, but then it becomes 0 if omega integrates to 0 along the whole line, then f becomes 0 at plus infinity again, so f has compact support, and we see that our form is exact. Okay, this is a very easy example, but we already see that the difference. And we immediately see that of course, compactly supported de Rham cohomology are not homotopy invariant. Well, R is homotopy equivalent to a point. For a point, we of course have point as compact. For a point, of course, we have such cohomology, both compactly supported or not compactly supported. There is no difference. But here we have different cohomology, so this is not a cohomology theory in usual understanding. There are no axioms, Stirner-Lindbergh axioms are not satisfied, and in particular, this is not homotopy invariant. And moreover, an important thing is that in compactly supported cohomology, there are no pullbacks. The matter is that if you have a smooth map of manifolds, you have a form here, and you take f star of omega. It is possible that omega has compact support, but f star of omega can have non-compact support. Well, just an easy example. We have a circle. Of course, on a circle, every point, every form has compact support. And here we have usual angular form d phi, where phi is polar coordinate. If you consider this standard map from line to the circle, so phi equals t, here we have coordinate t, and just t mod 2 pi. Okay? Then the pullback is usual form dt, which is not compactly supported. So there are no pullback in general. There are pullback if f star in compactly supported forms and hence in compactly supported cohomology is well defined if f is proper, where proper means that pre-images of compact sets are compact. If pre-images of compacts are compacts. Собственные. по-русски, собственное выражение. Вот. So if this property is satisfied, then of course, when we take pullback of a compactly supported form, we again get a compactly supported form, and everything works. But in general, it is not. And maybe even more important, how to deal with cohomology if it has no homotopy property, if it has no pullbacks, but an important thing that, a good category for usual cohomology is just category of smooth manifold. For usual de Rham cohomology, we just take category of smooth manifolds and their smooth maps. This is a usual good category for usual de Rham cohomology. For compactly supported de Rham cohomology, there is another very important category. Of course, we can consider category of smooth maps and their proper smooth manifolds and their proper maps, but actually we have an important smaller subcategory, which is also very most used. Usually, it is used in this formulation, that we can consider smooth manifolds we can fix of fixed dimension, M, and their impedance as open subsets, and maps are impedance. I'm sorry. I said this is a subcategory. This is not a subcategory. This is a different category. Impedance are not proper maps at all. So, of course, okay, if you consider just an open disk in Rn, then this embedding is not proper, of course. The preimage of a compact is the whole, can be the whole open disk. But what is important? Here we still do not have pullbacks, but here we have push forwards. The matter is that if you have an embedding from M to N, and M and N are of the same dimension, so embedding is just embedding to an open subset. Then you can just, the picture is like that. You have M inside N, and it is of the same dimension. And you have some compactly supported form on M. Then you can just extend it by 0 to the whole N. So there is this trivial operation, extension by 0. And we get a map from compactly supported forms on M to compactly supported forms on N. This is map in a wrong direction, in not usual direction. Usually we can restrict forms, but here we can extend forms by 0, and we get, of course, this map extension by 0 commutes with differential, obviously, and so this commutes with D, and so we get a well-defined push forward in compactly supported cohomology. And this is very important moment, and this is why it is interesting and convenient to work with compactly supported cohomology, since we have we still have good, not pullbacks, but push forwards in this important situation. Well, what else do we need about compactly supported cohomology? First of all, we need an analog of Poincare lemma. We have Poincare lemma in usual cohomology. Again, we have this with standard formulation that the Rm cohomology of Rn are trivial except for dimension 0. But we have somewhat more interesting formulation again, that if you have 0 section and projection, then they are mutually inverse in the Rm cohomology, and they are homotopically inverse in forms. So we would like to an analog of this assertion in compactly supported case. An analog is as follows. An analog is as follows. We cannot, first of all, what is our expectation? Our expectation, of course, is not the compactly supported cohomology, of course, are not isomorphic in this situation. We saw this when M is a point, then they are not isomorphic. And what is, okay, we have discussed compactly supported cohomology of R, but what is compactly supported cohomology of Rn? I don't want to prove it in detail now, but similarly to the R, we have N form which integrates to 0, and at least our hope is that it is R in dimension N, and it is 0 in all other dimensions. So we expect that multiplication by R provides isomorphism between nth cohomology and n plus first cohomology. So we expect that kth cohomology of M is isomorphic to k plus first cohomology of M cross R. And well, so we at least would like to have maps in both directions. Which are, what are maps from the left to right and from the right to left? First of all, it is easy to find a map from left to right. So, of course, maps, we hope to have these maps on the level of forms, and then we would like to prove that they are homotopically inverse to each other. What is map on the level of forms? So we would like to obtain a map from compactly supported K forms on M to compactly supported K plus 1 forms on M cross R. Well, how can we do this? This is rather easy. Again, let us fix a 1 form on R which integrates to 1. So we have choose some function with integral, a compactly supported function with integral 1, and we consider this form E, which is h of x dx. Just let us choose it and fix. Once we do this, we can just, well, if we have a form here, then we can map it to the form. First of all, well, I always denote this projection by pi. So we can take we can take pullback of this form, but it is not compactly supported. It is a bad form. Okay? we have compactly supported form on M. The picture is like that. This is M. We have compactly supported form, something here. But then we pull back to M cross R. So its support is non-compact in this direction. But now we can just take the product by E. Okay, it is better to say that it is projection. Well, I prefer to denote it. Let us use another letter P. This is projection to the second. To be precise, we take this P star of E, and this guarantees that our form has compact support in this direction, because E has compact support in this direction. And this is a well-defined map. Well, of course, let us call this map E star. It is induced by multiplication by E, so it is E star. And, well, it is easy to see that this map commutes with differential. Indeed, E is a closed form. So when we take the differential of this, we just need to take the differential of omega. So this commutes with differential, so this is a chain map. This is a chain map. Okay, we would like to have a map in the opposite direction. So we would like to have a map from compactly supported forms on M cross R to compactly supported K forms on M. How to do this? Again, any form, if we have, let us proceed locally in coordinates. If you have some, well, X is the total set of coordinates in M, and T is coordinate in R, then any form on M cross R, there are forms of two types. First of all, we can consider forms which have several dx's, and that's all, k plus 1 dx's. And we can have forms which have several dx's and also dt. Okay, and this map is called integration along fiber and along R. So if we try to integrate along T, then this goes to 0, and this goes to the form. Yes, of course, this form must have compact support in both directions, and this goes to the form. We just integrate this function along T, so this is local in coordinates, but it is easy to see that well, this is well defined, of course. If we change coordinates, then everything is okay. In fact, we can instead of this guy, we can write down any form, or it is more invariant form, that we take any form sitting only on M, and here also we have any p star of omega dt, and here just by omega. So we can write it in this form. Good exercise is that it is indeed well defined, and also it is rather easy to see. For instance, on local coordinates, it is immediate that p star also commutes with differential. So this is again a chain map. And we have two chain maps in opposite directions. These chain maps, they are chain maps between this chain complex and this chain complex shifted by 1. So there is such shift of dimensions, and this is one of the problems which I suggest you solve during our second hour. Problem is construct chain homotopy. Well, in one direction, the composition is just the identity. In which direction? If you first multiply by E and then integrate, then E integrates to 1 and we get just the original form. So if we take E star and then P star, then this is just identity. But if we take the composition in another direction, then it is not just identity, but it is homotopic to the identity, chain homotopic to the identity. So problem is to construct explicitly chain homotopy between the opposite composition and identity. If you do this, then you just get that these two maps are mutually inverse on the level of cohomology. So on the level of cohomology, we just get isomorphisms. This is isomorphic to compactly supported cohomology of M cross R. And in one direction, here this is multiplication by E. It is better to write by P star over E, but in fact we can do like that. And in opposite direction, it is integration along fiber. Okay, this is an important thing. This problem we discussed during the second part. And what is next important fact? Next important fact, of course, consequence of this is that the de Rham cohomology of Rn are indeed, as I claimed, proceeding by induction. We can say, starting from here, since we have this isomorphism, we can say that compactly supported de Rham cohomology of Rn are indeed R in dimension n and 0 otherwise. But also an important thing is that in this situation we also have Meyer-Vittorius sequence. But again, this sequence is in the opposite direction with respect to the usual one. When we have what is the situation when we have Meyer-Vittorius sequence? The situation is that our manifold is the union of two open subsets. Yes? So suppose that M is U cup V, and in usual, then we can consider this intersection. We have impedance I1 to U, I2 to V, and then impedance, all these are impedance, to M, this is J1 and this is J2. Let us introduce this notation. When you consider usual forms, just not compactly supported, but all differential forms, then you have pullbacks along these maps. And what was the exact sequence. We had exact sequence like that. We take forms on M, then we restrict them to U and to V, and take here G1 star plus G2 star, which gets to forms on U plus forms on V. And then you take I1 star minus I2 star, which gets to forms on the intersection. Well, this is usual, and we have proved last time that this sequence is exact, and hence it uses standard Meyer-Vittorius sequence in cohomology. What happens in compactly supported cohomology? In compactly supported forms, we do not have maps in this direction, but we have maps in the opposite direction. We have push forwards along embeddings of open subsets. So we have maps like that. We can take first compactly supported cohomology of the intersection. Then we can take I1 push forward minus I2 push forward to compactly supported cohomology of U plus compactly supported cohomology of V, and we can take J1 push forward plus J2 push forward to compactly supported forms on M. So all maps are in opposite direction. It is not important where we take minus and where we take plus. It is important that in one situation it is minus and in another it is plus. Okay, so proposition that this sequence is exact. This is a short exact sequence. And it is even easier than in this situation. We have some problems with it was not so obvious, but here it is completely obvious that it is exact. Look, okay, why it is surjective? If we have a compactly supported form on M, how can we obtain from it two compactly supported forms which together give this form? We just, if we have this form, we just take, as usual, partition of unity and take these are compactly supported forms on U and on V respectively, and of course their sum is just omega. So this is why it's surjective. Injectivity here is obvious, and why we have exactness here. Okay, if you have two compactly supported forms that together give 0, then they're equal. One is equal to minus second, and so their support is indeed contained in the intersection, since they coincide, and so we get a form from here. So it is completely obvious that this short exact sequence is exact, and once we have this, we get the Meyer-Vittorius sequence. In compactly supported cohomology is like that. You start from kth cohomology of the intersection. You go to kth cohomology of U plus kth cohomology of V, then you go to kth cohomology of M. Well, these maps are as there. I start this one and this one. And then you have this map T star. In this situation, lower star is used. It gets to K plus first compactly supported cohomology of U. Well, and so on. Well, we have here some non-standard situation. Standard Meyer-Vittore sequence in cohomology goes in the opposite direction. Yes? Standard Meyer-Vittore sequence in homology goes in this direction, but then we have the degree reduces by 1, but not increases by 1. But here is just that situation, that sequence is in this direction, but the dimension increases by 1. Okay. And again, as in the previous situation, we can immediately write down this star. And it is important to keep in mind that we can not only say that such map exists, but we can write down it explicitly. Well, why? How this star works? We take the pre-image of omega, then we apply D. Even if the form was closed, by no means these two forms are closed, so they are not generally closed. We take the differential and then we take a pre-image here. And so it is easy to see that this is just the cohomology class. It is just the cohomology class of differential of rho u times omega. It is minus the cohomology class of the differential of rho v times omega. Look, omega has compact support in M, yes? But when you multiply it by rho u, you get compact support in U. Maybe not even compact support, just we take any form in U, yes? But then the differential of it has only compact support in U cap V. The matter is that, look, outside some compact region in the intersection, outside some region, not necessarily compact, outside some region in the intersection, rho u and rho v are outside some such region. Rho u and rho v are constant, and since omega was closed, this differential is 0 outside such region. Then omega has some compact support like that. And so this form has compact support here. Okay, but actually it can be seen from this exact sequence that this is in fact a form with compact support, but it can be seen thus explicitly as well. Okay, so we have Meyer-Vittore sequence.
Sorry, why rho u of omega have compact support there?
Rho u of, well, here, yes. Because its support is contained in support of omega. Well, yes, that's a good question. That's a good question. Okay, the matter is that yes, the support of U. Let us discuss it in detail. Indeed, the support of U was some compact in M. Yes. The intersection of a compact in M with U can be non-compact in U. Yes? So if we take the intersection of a compact with U, yes? Then it can be non-compact. But can be non-compact in U. But if it is non-compact in U, then it has a limit point which does not
can you simply say that rho U has closed support in U?
Yeah. Thank you. Yes.
It is the intersection of the supports of rho U and
yes.
W. One of these is compact over the whole M, and rho U is closed in V.
Yes, I'm sorry. I have some problems with maybe an intuitive answer is that the support of indeed the support of rho U. Well, if this is U, this is V, well, then why a compact set, if we have some compact set here, then it can becomes non-compact in U if it has a limit point which doesn't belong to U, if it has such limit point. But then in this limit point, rho U is 0 in the neighborhood of this limit point. So we have no such limit points in the support of U. This is not very precise, but a good exercise to make it strict proof. So I prefer to leave it as exercise than to discuss such. This is some questions of general topology, which
precisely that the support of rho U is separated from the complement of V.
Yes, that's something like that. Yes, the support is separated from the closure of M with U. The support of rho U is separated from it, and that's enough. Yeah. So it is not hard, but I don't want to do it just now in detail. Okay. Okay, that's good. We have this Meyer-Vittori sequence. Why this Meyer-Vittori sequence for compactly supported cohomology is important? It turns out that there are several important facts which can be proved by induction. In the following way. We would like to prove some facts about a manifold, and we consider cover of these manifolds by an open cover of this manifold by open sets, and we would like to say that okay, some assertions can be proved if we know some assertions for U cap V for U and for V, then you can prove it for M. This is general strategy, And to realize this strategy, usually, what is the simplest manifold? The simplest manifold is Rn. If you have Rn, then, well, you can check everything by hand. But then you can consider covers by contractible sets. Well, okay. Not only of course, if two manifolds are diffeomorphic, then the cohomology are the same. So you can, for all manifolds diffeomorphic to Rn, the cohomology are known. And the general strategy is to consider the covers such that, but look, if you want to proceed from sets, from two, say sets to their union, you also need to care about their intersection. So a good situation is that not only cover, elements of the cover are diffeomorphic to Rn, but also intersections of them are diffeomorphic to Rn. This leads to the following definition. The following definition. That an open cover U alpha of M is called good. This is a technical definition. This is not, a terminology. This is just what is convenient to say for this moment. If all non-empty intersections of several elements, so the intersection of several elements of this cover is either empty or diffeomorphic to Rn, where n is the dimension. So assume that we have this situation. Assume that you have this situation. A standard lemma is that first, any manifold has a good cover. And second, any compact manifold has a finite good cover. Any compact manifold has a finite good cover. Of course, second one is an immediate consequence of the first one. If we have a good cover and a compact manifold, then of course you can consider finite subcover. So we need only to prove the first one. I don't want to prove it in detail, but okay. The idea behind it is that we can always endow a manifold with a Riemannian metric. And if you choose a Riemannian metric and consider a very, very small neighborhood of a point, then the metric is arbitrarily close to the Euclidean one. If you just consider with and then consider a homotopy of the metric so that this small neighborhood becomes say, of diameter 1, then the metric becomes arbitrarily close to the Euclidean one. And then it is a standard fact, which I don't want to prove. Here it is of different type than this course. It is a standard fact that balls become, balls in this metric, small balls, become geodesically convex. Well, usual balls in Euclidean space are convex. And if the metric is arbitrarily close to the Euclidean one, then they are geodesically convex. So for each 2 points, first of all, if 2 points are close enough to each other, then they are connected by a unique short geodesic. And second, this geodesic is inside this ball, and okay, if any point has such a neighborhood, then these neighborhoods form a good cover. The matter is that they intersect. If they intersect, then again we have here all points are connected by geodesics, so you can choose. If you have intersection of several such sets, then their intersection is still geodesically convex. And if a manifold in an open subset of a manifold is geodesically convex, then it is diffeomorphic to Rn. The matter is that you can just consider all geodesic from that point and renormalize its geodesic so that it goes from 0 to infinity, and then you get a diffeomorphism from Rn to this region. Okay. So this lemma is more or less immediate if we know these basic properties of geodesics. And once we have this lemma, we will usually work one more definition. We say that a manifold is of finite type if it has a finite good cover. All compact manifolds are of finite type, but also some non-compact also have non-finite type. For instance, Rn is of finite type. Well, M is of finite type if M has finite good cover. And okay, if M is a finite type, non-strict statement, but in fact all interested manifolds are of finite type. We very rarely are interested in something that is not of finite type. Usually manifolds can go to infinity. We often deal with non-compact manifolds. Okay, for instance, if you have a smooth compact manifold and a vector bundle over it, then it is not compact, of course. And there are plenty of situations when we need to work with non-compact manifolds. But it is very non-standard situation that you need to work with manifolds which are not of compact type, usually of finite type. Usually all manifolds which arise in nature are of finite types. They have some ends on infinity which are not so interesting. And of course, this is not a rule. It is rather easy to construct a manifold which is not of finite type. Just consider plane without series of balls, infinite series of balls. Of course, this is not of finite type. But usually there are a lot of manifolds which are of finite types. And if a manifold is of finite type, then there is the standard Meyer-Vittoris induction. To prove some assertions, we can proceed by induction on the cardinality of good finite good cover. So Meyer-Vittoris induction is Meyer-Vietoris induction is nothing but induction on the cardinality of induction on the cardinality of finite good cover. So if you have finite good cover, base of induction is always Rn. If you have finite good cover of one piece, then just your manifold is diffeomorphic to Rn itself. It is one piece and it is diffeomorphic to Rn. And then assume that our manifold has a finite good cover of, say, m capital pieces. Then you can consider two subsets, U1 and the union of all others. And this union of all others has finite good cover. U2, Un are just finite good cover consisting of n-1 subsets. But, which is important, the intersection also has a finite good cover consisting of n-1 subsets. Namely, we can take these n-1 subsets, and this is also, by definition, this is also a finite good cover. So we see that once we have a manifold with finite good cover of cardinality n, we can always decompose it into two open subsets such that each of them has complexity smaller. Here we have finite good cover of one piece, and here we have finite good cover of n pieces, and in the intersection we n-1, and here we again have finite good cover of n-1 pieces. So we can proceed by induction. If we do the following, we only need to prove if we want to use this induction, we want to prove that okay, once we prove some assertion, we want to prove that if this assertion is proved for U and for V and for U cap V, then we get this assertion for the union. Once we have proved this, we immediately obtain the assertion for all manifolds of finite cover. This is standard strategy of finite type. This is standard strategy. The next part of this strategy is usually taking some limit for manifold of non-finite type, but we will not deal with this. I will prove results only for manifolds of finite types, though they are usually true. Some of them are true for manifolds of non-finite type as well. Okay, let us start with the first assertion, which can be proved in this way, is very easy. And this first assertion is not true for manifolds of non-finite type, of course. So the first theorem is that if M has finite type, then the de Rham cohomology groups of M and de Rham cohomology groups with compact support of M are finite dimensional. Well, I even don't want to do anything with the proof. I just want to say that it is obvious. It is true for Rn. This is base of induction. And of course, if this is true for U, for V, and for U cap V, then the same is true for their union. And it follows immediately from my arbitrary sequence. If you have a non-exact sequence and you have finite dimensional groups on these positions, then here we again have finite dimensional, of course. Yes? So this is just immediate consequence. Well, this is an easy thing, but it's almost time to finish, and just I want to formulate the. I'm sorry. Today I wished to say. I thought I will have time to say more, but okay. The next theorem. If M is oriented and has finite type, if M is oriented, let us say that it is connected and oriented and of finite type. Then we have the Poincare duality. Poincare duality is a standard. Usually Poincare duality is isomorphism between cohomology and homology. In our situation, we do not have homology at all. We have only cohomology up to now. So this is not isomorphism, but this is pairing between cohomology in the corresponding dimensions. Moreover, usually Poincare duality is for compact manifolds. For compact manifolds, in the simplest way, compact manifolds without boundary. Yes. In our situation, I do not require M to be compact, and actually, if I require M to be compact, I cannot proceed by induction at all. All our base is for non-compact manifolds. So even to prove Poincare duality for compact manifolds, we need to formulate it for non-compact. And a good formulation for non-compact is that we have a non-degenerate pairing between usual cohomology and compactly supported cohomology of complement dimensions. So there is non-degenerate pairing, and this pairing can be written immediately on the level of forms. If you have a K form phi and a Nn minus K form psi of, well, what does it mean non-degenerate pairing? It means that bilinear pairing such that both left and right kernels are trivial. Yes, here we have not compact support, and here we have compact support. It doesn't matter which of them is compactly supported, of course. If you have two such forms, then we can write it on the level of forms. So if you have cohomology classes of two forms, but this form is arbitrary and form psi has compact support, then you can map it to the integral over M of the product. The product has compact support, and you can integrate it over M independently of whether M is compact or not. So this is the definition of pairing. Obviously, if one of the forms is exact, then this pairing is 0, so this is well defined. If one of the forms is exact, then the product is exact. Well, so this is well defined on the level of cohomology, but the claim is that the only non-trivial part is that this is non-degenerate. And we will prove it next time, but the idea is just that if it, the idea is the same, that we just use Meyer-Vittori's induction. We know this for Rn, we have already, for Rn it is trivial, and then we proceed, if we have it for U, for V, and for U cap V, then just by some diagram technique on exact sequences, we immediately get it for the union. Okay, so let us have a break now, and that's all for today.
Можно ли каким-то образом говорить о, думаю, вероятности симметрии?
It's time to start. Sorry. Well, I have some list of tasks for today. It's better to use this, though I don't think it is quite reasonable for seminar, since I mostly be silent. Okay. I have some list of tasks for today. Actually, one maybe. Okay, can you spread it? In fact, last time, I would like to recall that last time we concentrated on the problem of constructing explicitly a form. We would like to construct a closed to form on CPN, which is closed, and generate the second cohomology. And the idea was to consider the action of unitary group, well, or projective unitary group. This acts on CPN. It acts on Cn plus 1 and hence on CPN. And the idea was to consider invariant forms. With respect to this group. Actually, I claim that I hope that you do this, that an invariant form is unique up to multiplicity and up to a constant, and actually it is closed and it generates the second cohomology group. And the idea was to do this explicitly, but if you look in this list, then okay, actually the first problem is some basic thing which I skipped last time. I skipped the proof that I said, okay, if we have a form, yes, if we have a closed form, which is not invariant, then we can construct an invariant form by averaging along a group. And I claim that it generates the same cohomology class. So the first problem is just to prove this carefully. And the second problem is just to apply this to CPN. There is a more toy situation, simple situation, when you can apply this to the torus, and it is completely easy. But CPN is interesting case. RPN is somewhat more difficult case, but still not so much. So have anybody finished this computation with CPN which we started last time?
Finishing means that explicit formula.
Yes. It would be nice just to write down this omega. So we have two tasks. First, we would like to prove that indeed, in general situation, if a compactly group, this is just task 1, compactly group acts on some manifold, and if we average along this compactly group, then we again get. If we start from closed form, then we again get a closed form, and it has the same cohomology class. This is just some first problem. But the second problem is just to write down this form explicitly on CPN. On CPN, it's on an explicit manifold. It is very good to have explicit answer.
How understood before, it is the same as in our case to find some skew symmetry to form on just usual space where we have a Hermitian form.
Yes. That's actually our the idea is that we have Hermitian form and we would like to have skew-symmetric real form.
I was trying to do this, but I have a problem that if we have point, like we have chart 1, the first experiment is 1, and then
Yes.
that 1 is the 10. Then we have, well, in point 0, 0, 0, we have form like regular E times there's a bar, and then we have map from 1, 0, 0, 0 to 1 z 10, which is clear how to construct. But this map induces pullback of form, but not push forward. And to get push forward, we should use inverse.
The inverse map, yes.
Map, but it's hard to understand. We should write it.
If you can write it in one direction, then just solving equations, you can do it in the opposite direction. Yes, problem 5, just skip it. The matter is, I was sure I still do not tell you anything about some class, so it's not for today. I hoped I do it, but not. So I suggest you try it to do for some time, and then we discuss what. Напишем сегодня явно. Напишем сегодня явно. Сейчас посмотрим.
Inverse map is like транспонированный из призма на живота.
Yes. So actually, I would like to say one easy thing. Then, okay, it is not convenient to work with projective unitary group. It's some small difficulty that we have not unitary group, but projective unitary group. Yes, and it is not so easy, not so pleasant to work with something like that. But you can just skip it. The matter is that unitary group also acts. It is also compact, and it is also acts on Cn+1 and hence on CPN. The matter is that diagonal torus here, diagonal circle, acts trivially, but it doesn't matter. You can average along this larger group. So just don't think about projective at all. It's okay to work just with unitary group. This action is not effective, but it is more convenient than the action of projective. So we discussed the strategy last time that we have a nice point in CPN is point 1, 0, 0. Yes, this particular point. We first would like to construct a two form is a skew symmetric two form. So we first would like to construct a skew symmetric bilinear form on this tangent space. Well, let it be P0. We would like to construct a skew symmetric bilinear form on this vector space, which is invariant with respect to the stabilizer. So it is invariant with respect to UN is the stabilizer of this point, which acts on the complement of the first vector. And then we just would like to extend it to the whole CPN by other unitary matrices.
sure.
We can choose some basis like this. Мы можем такую форму, такое представление взять для обычной эрмитовой формы. Но если мы симплектическую такой же образом зададим, то она будет инвариантной. То есть она будет как-то вот такой матрицей задаваться. Ну, какой-то классической такой. То есть формитор будет такой.
Нет, хорошо, в каких-то координатах она, конечно, так будет, но вот хочется же явно это на CPN написать.
Просто его еще явно как-то
да.
То есть это просто вот такое.
Да. Нет, хочется, чтобы с этим мы могли работать. Например, сейчас захотим ее возвести в степень и проинтегрировать по ЦПК. Хочется научиться ее действительно явно писать в координатах. Это тот случай, когда ее в таком базовом стандартном случае действительно хочется явно взять и написать.
Просто не совсем понятно, если в явных координатах, как мы видим действие у лям.
Так вот оно в координатах и действует. The idea is, what do we want? We want not, okay, here we have, for instance, non-homogeneous coordinates, yes? We have homogeneous coordinates, and we have non-homogeneous coordinates, let it be zi capital, which are, okay, we would like just to write down this form in this non-homogeneous coordinate, just as it is two form. So it is better to write in homogeneous coordinates, of course, but let us begin with writing it, okay, in these non-homogeneous coordinates, just explicitly. It is very particular form. It is very, very nice particular form. So it is not something abstract. It is just one particular thing. It's we would like to have just explicit formula. So it should be something like, okay, omega is some particular function, something like that.
So in our case, we take coordinate like the and the conjugated. Yeah?
Yes, of course. We are. What we want just a real form. So of course we can use both zi and z conjugate I, and okay, do you have at least this form in this point?
Yes.
And okay, can you tell us the answer?
It's standard form like I times desert E bar, or we can write some dx j match dx j.
Yeah, so in this particular form, our form at P0, yes? In non-homogeneous coordinates, in this Z capital, yes? We would have just something like there's a J, let us use J for safety, not I, times Okay, if you take something like that, it is not real, yes? The matter is, it has, you need to write something like that, yes? Then it becomes real. Okay?
Then we understand by group action.
Yes, and now we would like to, yes, we would like to transfer it to all points and to get a particular answer in all points. So this is actually one more thing. Is it clear that this is a unique form up to multiplication that is invariant? That's also. If you don't understand, then it is a good point to think also that this is not only some form which is invariant, but this is a unique form which is invariant with respect to un. Of course, up to multiplication by a constant. And now we would like to extend it to the whole CPN, and to obtain an answer in some very explicit form, like that.
I understand it would have the same form on the whole chart where Z0 is non-zero.
No, it is not the same. If you apply this one behaves well with respect to the action of un, which stabilizes this. But if you apply, look, if you apply un plus 1, then you need to, how to apply un plus 1 here? You need to come to homogeneous coordinates, then apply a matrix, then again return to non-homogeneous coordinates. So you, in these non-homogeneous coordinates, un plus 1 acts by not linear formulas. It acts by fractional linear transformations. And if you apply this fractional linear transformation, then this form is not invariant with respect to the whole group. It is invariant only with respect to un. Un acts by true linear transformations in these non-homogeneous coordinates, and it is invariant. If you take the whole group un plus 1, it acts by fractional linear transformation, and that one is not invariant. So this is a good answer only in this one point. So here must be some coefficients which are maybe polynomials or some other function, some functions of that I, which and we know these functions in one particular point at present.
Not the 1 plus sum of the squares.
I just didn't did it, but
No. Well, the good idea here is that it is very inconvenient to work with the whole group un plus 1 in non-homogeneous coordinates. So I suggest you come to homogeneous coordinates and rewrite this formula in homogeneous coordinates. And maybe it will become easier to understand the answer. For the whole group action, homogeneous coordinates are better than non-homogeneous.
What does it mean to write form in homogeneous coordinates?
Okay. We'll just substitute here those expressions. If you have a function, yes, of course, this j is not small j, is not a good form on CPN, yes, but it is a good form. Well, CPN is Cn plus 1 is the quotient, yes. Still it is a good form on here, and still it is convenient to not every form here goes to a form on CPN, only those which are invariant with respect to the torus, this algebraic torus. But still invariant forms on CPN, it is convenient to write them here, to write them in these homogeneous coordinates. So
То есть, как я понял, написать однородную форму, это все равно, что однородную на обычном векторном пространстве, но вариант. То есть, это будет корректно.
но это все равно, что написать форму вот здесь, которая инвариантна и относительно унитарной группы, и относительно гоматетии. Еще дополнительно.
Ну, например, понял, как инвариантно написать.
Yeah, once more, the idea is that how to write a form on CPN. Let us write a form on this, on Cn plus 1 without 0, which is invariant both with respect to unitary group and with respect to multiplication, scalar multiplications by const. Well,
Будет, ну, как бы берем сумму ко всем заитам, делим на квадрат, ну, на сумму квадрата, потому что, ну, когда гоматетии тут как бы лямбда штрих выскакивают, и тут, соответственно, соответственно, ну тут модуль, поэтому как бы это одно и то же. То есть сокращается.
Ну, относительно гуматоитин вариантно.
Да.
Относительно
Эта вещь, она сохраняется, а это же просто сумма, ну, вот такого вида. А это как бы, ну, в некотором смысле то, как мы вообще записываем эрмитовую форму. Ну, она как бы должна сохранять вот эту норму.
Сейчас, подождите секундочку. Что-то не так.
Ну, то есть, по сути, это просто записывать, ну, как бы вот, что-то в таком духе. Ну, она инвариант. Вот.
Сейчас, одну секунду.
Ну, мы как бы тут с нуля с вами.
Угу. Сейчас почему нет, не нравится? Или оно так и было? Забыл. Сейчас. Подожди. Ой, извините. Я сам себя запутал. Сейчас, извините, я это банальную вещь забыл. Так. I'm sorry. It is not enough. I forget a very important thing, which is very easy. It is not enough to write down a form once more. CPN is, of course, such a quotient. And I would like, I said you that, okay, to write down form here, we would like to write form here, which is invariant both with respect to unitary group and with respect to multiplication by scalars. It is not enough to write down such formula. We need one more restriction. The matter is that, okay, look, here in the quotient we have CPN, but upstairs you have this Cn plus 1 times 0, and here you have one-dimensional fibers that go to points here, yes? if you have a form on CPN and pull back it to Cn plus 1 without 0, it must be 0. Vectors tangent to fibers must be in the kernel. We have such restriction. Vector tangent to fibers go to 0 downstairs. So they must be in the kernel. So we would like we would like a form upstairs that satisfy the following conditions. It is invariant with respect to unitary group. It is invariant with respect to multiplication by scalars. Yes? And third, it is 0 tangent spaces to fibers lie in the kernel of this form. Yes? Your form satisfies the first two conditions, but not the third one. That's become the reason why it is not the correct answer.
Это, как я понял, третий, это, то есть, можно какое-то явное векторное поле выписать и что-то там условно.
Yes, it is rather easy to write down this formula, this vector field explicitly.
Sorry.
It is just well, how to write down this vector field. If you have coordinates z0, zn, coordinates just in Cn plus 1, yes? Then it is just a vector field with these coordinates at each point. Yes. Да. Ну, вот у него такие координаты и есть. В точке z0, zn.
Вот третий условие, на самом деле, если думаться, ну как бы...
Этот вектор должен с любым другим вектором 0 давать. Он совсем в ядре должен лежать. Ну, потому что иначе она не опускается вниз, ваша форма. То есть, как бы ваша форма вот не опускается на CPN. Она вверху хорошая форма, но на CPN такой формы просто нету. Она не 0 на том векторе, который в 0 уходит. Да.
Но это не в одной, например. Вот если у меня есть отображение f, у которого мы знаем, что дифференциал вот так записан,
так.
И мы знаем, что вот здесь есть форма, которая тоже понятно записана.
Так.
Тут я еще туплю, можно как-то просто что-то во что-то подставить и раскрыть скобки, чтобы получился pullback. А то, если явно писать, что какая-то фигня получается.
Сейчас, у вас отображение в эту сторону, да?
Угу.
Дифференциал. Сейчас, подождите. По вектору здесь вы умеете писать вектор здесь, да?
Угу.
Ну так его надо подставить в эту форму.
Да,
но вы получите форму здесь. Нет, ну как бы.
Тут как будто просто выглядит, что можно что-то
можно угадать просто. Можно просто угадать, как она выглядит. Вот из вот этих вот трех.
Почему вы говорите, что имеется в виду, что вот этот слой он на сфере? Или он тоже двумерный?
Ну, он двумерный, поэтому, да, на самом деле, да, этот вектор и на этот вектор. Да. Двумерный, конечно. Да, он комплексно одномерный. Естественно, двумерный. Ну вот, да. Yes, this fiber from real viewpoint, it is two-dimensional. It is one-dimensional from complex viewpoint, so both these vectors should be in the kernel. Both these vectors should go to 0.
sorry, when you write that z0, z0, когда вы пишете z0 или zn это какой-то вектор, кстати, это имеется в виду...
Нет, ну это в cn плюс 1. Это просто в cn плюс 1. Давайте забудем про CPN, чтобы не мучиться let us forget about CPN. No, not to deal with any. Let us consider Cn plus 1. Just vector space. You have this Cn plus 1. This is schematic picture, but this is picture for Rn plus 1, yes? That you have fibers here which go to 0, which each fiber goes to point when you pass to CPN, yes? So here you have vector. If this point has coordinates z0, zn, then this vector has coordinates z0, zn. This is just the same coordinates. And also, but still you are in complex situation, you also have this vector, it is also tangent to the fiber. So we would like to have a form, just a form in Cn plus 1, which can be written in these coordinates z0, zn, skew symmetric form, which satisfies these three conditions. It is invariant with respect to the unitary group, it is invariant with respect to multiplication by scalars, and these two vectors must be in the kernel of this form. This is then we can put this form downstairs to CPN. Well, what is the form on CPN? If you have two tangent vectors here, you go upstairs and then compute the form. But when you go upstairs, these lifts are not unique. They are unique up to those two vectors. So if those two vectors are in the kernel, then it's okay to take lifts and to compute the form. If they are not in the kernel, then it's not okay. Okay, maybe I just... простите, я не знаю, как вас зовут, вот вы мне... Денис. Вот Денис написал... Денис suggested form which satisfies two first conditions. It is rather easy. It's just... and 1 over e to get it real. Okay, this form satisfies, it is obviously invariant with respect to unitary transformations, and it is invariant with respect to multiplication by scalars. It can be seen directly. But this form doesn't satisfy the third condition. Those two vectors are not in the kernel. But we need to do something with it.
Можно вопрос? Когда мы говорим, что у нас в точке z0, zn есть касательный вектор с координатами z0 или zn.
Да.
Что это система координат на касательном пространстве?
Well, actually this is... like that, something like that, or not? Okay. It is in real. Let us... this is a good question, and if you answer it properly, then it will help you. In a real situation, what does it mean? What are real coordinates? Real coordinates are, you need to introduce coordinates like that, yes? Then, what does it mean, points z0, zn? You have, this is point like that, xn, yn, okay? What does it mean that you have vector with those coordinates? The standard basis is like that. Yes? So vector with these coordinates is just the vector and now let us rewrite it in complex coordinates back. And it should help you if you do it. Well, actually, one more hint. How to write down this formula? What is written here? You just, if you have, actually, what is a skew-symmetric form on Cn plus 1 times 0? Actually, this is a function on vectors, yes? First of all, we would like to have a skew-symmetric functions. So we would like to have function of two vectors, yes? We can write it in coordinates, but we would like to have a function which is bilinear skew-symmetric. Well, how to rewrite this in this situation? And of course you have not only, so you have point, let us denote this point by z. z0, zn are its coordinates, but you have this point z. And you have here two vectors, xi and eta. How to rewrite what is written here? Well, this function. This is not the correct answer, but this function. What is written here? This is imaginary part of we can take Hermitian scalar product, yes? Mm-hmm. And what is written here is imaginary part of this, yes? But then divided by Hermitian scalar product of the z with itself. Yes? This is exactly what is written here. Okay. If we look on this picture, then it is completely obvious that it is invariant with respect to the unitary group, since both parts are in, and it is invariant with respect to the action of C star, because if we multiply both vectors here and point here by the same number, then it's okay, yes? So invariance is obvious here. But what is not good? The matter is that if you take for xi, say, this vector, then it is not necessarily 0. What is the idea? How to correct this formula? How to correct this formula to get invariance, but to get that tangent vectors to here are in the kernel.
maybe add something like, no, we take only over, no, the same pair, EE, no, in some sense. Maybe add something like, no, EG pairs, no, or
Нет, ну вот на этом вот языке гораздо проще. Вот у вас вы делаете, это не надо никаких координат писать, надо писать инвариантные вещи. You need not coordinates, you need just, this is some invariant thing, yes? But what else invariant can we do to obtain that tangent vectors are in the kernel? Ну как получить какую-нибудь билинейную форму, чтобы вот данные векторы были в ядре? Надо их как-то убить.
А вектор наш явно выглядит как сумма, ну, по всем координатам.
Ну, потом в координатах напишем. Потом в координатах напишем, когда...
Взять это скалярное произведение, один вектор поставить, потом отнять квадрат скалярный.
Ну, умножить на форму, которая один форму, ну, на какой-то линейный функционал, который убивает этот вектор.
Тогда будет не билинейное.
Тогда будет не билинейное, да.
Ну, самое главное вычесть произведение двух скалярных произведений.
Ну да.
Как?
В смысле, вы subtract the product of scalar products of these two vectors separately by our.
So once more, you have three vectors in C n plus 1. Z, Xi, and eta. You need to write something through these three vectors. Something like that, but not that. But
Скалярное произведение Z с Xi на скалярное ZC поделить на ZZ.
You can write something like this. Yes? Then, okay, this is also invariant, yes? Mm-hmm. This is not skew-symmetric. No.
That's what they meant.
That's not, yeah, okay, I didn't. That is also invariant, but it is not skew-symmetric, the problem is, yes? Mm-hmm. But okay, it is invariant. And maybe we can combine something from that too.
We can write swap Z and Xi, for example, and take imaginary part.
Yes, that's a way to take. This is again Hermitian form. Yes. Now. Initially it was not Hermitian, but now it is Hermitian. Yeah. Okay, and we can take imaginary part, and it is again skew linear. Yes? Mm-hmm. So we have two skew linear forms, and the idea is to combine them so that both of them are invariant, and the idea is to combine them so that.
Если их вычесть просто сейчас, то если там Xi это Z, то получится 0 сюда. А если I Z,
Можешь вычесть одну и другую.
Well,
да, вычесть просто.
Okay. If you take Z for Xi, you indeed always get 0, yes? If you just substitute here Xi equal to Z, then it's 0. And if you take eta, okay, it is skew-symmetric, so eta equals Z against. But if you take Xi equals IZ,
The same because
it is again 0.
Yeah.
So it's,
It doesn't matter which number.
well, yeah.
The number will be changed.
Yeah. So, okay, this form satisfies our requirements. Okay. Well, but actually, I waited that you invent a geometric idea. A geometric idea was very easy. Well, how to get a bilinear form which is definitely 0 on a two-dimensional space. Let us project our vectors on the orthogonal complement and then take their... a true idea is the following. Okay, you have this two-dimensional vector space spanned by Z and IZ. Yeah, well, let it be U. It's a real vector space span over reals of Z and IZ. Well, then you can take, and you have here, this is Z, and you have here two arbitrary vectors, Xi and eta.
Что-то типа проекции.
Yes, you can take projection of Xi on the orthogonal complement. Let us take projection onto orthogonal complement of this U of Xi and take projection on this orthogonal complement of eta. Then you take this Hermitian form, take imaginary part and divide by ZZ. And if you write it down, it's exactly the same. But up to me, it is easier to invent this thing. So, okay. And look, in that particular case, in the point 1, 0, 0, 0, you get just that form. Well, I suggest now to write it in this form, to write it through coordinates. Now when we understand it in invariant form, let us try to write it in coordinates still. But that's the answer. Actually, if you, yes, it's better to divide by I to get real form, okay? But if you delete here imaginary part, then this is called the Fubini study Hermitian metric on CPN. This is Hermitian metric on CPN, and as usual, real part of Hermitian metric is Riemannian metric, and imaginary part is skew-symmetric form. What? Well, now what we want? What is our plan? Plan is first write f in coordinates, and why I suggest to write it in coordinates. The matter is that we still need point 2. We want that to understand why this form is closed. Now we get a well-defined form on CPN. It is invariant with respect to it is 0 on this space, and hence it's well-defined form on CPN. but we still do not know why it is closed.
You can understand it without coordinates.
Well, we can, but actually it's in this particular situation, it's, first of all, it is rather pleasant to have it in coordinates. The matter we would like to integrate it. We still need it in coordinates.
Можно доказать, ну, можно сказать, что просто у нас не может быть, то есть, если бы она не была точной,
замкнутой,
то ее дифференциал был бы 3 формы не нулевой, которая была бы инвариантом относительно действия P у n плюс 1.
Да.
И там, ну,
можно доказать, что такого нету, да. Да, можно показать, что такого нету. Ну, это отдельный вопрос, да, можно. Well, indeed, you can, in general, say that if this was not closed, then its differential was at 3 form, which is invariant with respect to projective unitary group, and there are no such 3 forms. But up to me, it's simpler to take the differential explicitly in this particular station, and in any way it is useful to write it in coordinates. Take first we would like to integrate it. Well, okay, this is 2 form, so we can integrate over 2 manifold, and it is naturally to integrate it along CP2 inside CPN. CP1, yes, sorry, of course CP1. And next, moreover, we would like to take powers of it and integrate it along CPK. So it's better to have it explicitly. And well, so yes, and the question is why it's closed.
Not exact, yeah.
But yes, not exact, because its integral will be non-zero. So we get this form, let it be omega, yes? We prove that it is 0 by differentiating. But third point, we would like to compute the integral over CP1, standardly embedded to CP2 of this omega, and we will get non-zero. And that's why, if it was exact, then by Stokes' theorem we would get 0. So it is not exact because of that. Yes, I add here 1 over I. That's what we want.
If we take imaginary parts, why should we divide by I?
Well, yeah, sure. We do not need to. Sorry. It's not yes, imaginary part, it's already divided by I, so it's okay. Yes, so, well, just the idea is just to write it down. In some. Well, just if it's difficult to do it in coordinates zj, you can do it in coordinates xj and yj. So just to avoid usage of complex coordinates at all, you can write all this, guys, in these coordinates. And then you may return back to topology. Well, sorry, I asked you an easier question. Suppose you have a Hermitian form on Cpn plus 1. Can you write it down in coordinates?
No, it's just there's the E conjugated.
Okay. Like that, yes? It is sum over G, yes? Okay? So, okay, it depends on I write it as that is linear on the first coordinate and anti-linear on the second, but okay, otherwise you need just to skip. It is, I'm sorry, it is not good. Actually, it is form of two sets of coordinates. You need coordinates of vector xi and coordinates of vector eta. Yes? So, if xi has coordinates, that's exactly mean that this one is applied to coordinates of vector xi and this one to vector eta. Yes? Now, what does it mean that you take imaginary part of it?
No, it is we take skew.
Well, what is imaginary part? Imaginary part means that you take this function, yes, minus this function, and you divide by I, yes? this means that you take 1 over I, this is J tensor, this is J bar, yes, minus this is J bar tensor, this is J. Yes? The reverse.
This is by definition.
It is by definition, and this is by definition the skew. We just this alternation is by definition the. It depends. There are two approaches. Should you put here 1/2 or not? But it doesn't matter. We just want to write it up to. I don't want to think about it. Okay, so you do it, this is how to rewrite this thing in coordinates, yes? But can you do the same with the second part? Okay, actually our time is over, so, but we have done the most difficult part. This is the answer, but now just you need to write it in coordinates, and then just to compute the differential, it's just simple computation that it is 0, and this is not as easy computation, but this is not hard computation just to compute this integral. It is just two-dimensional integral, very explicit, and it is not hard to compute it. And I suggest very much that it would be nice if you do it up to next week, and we can discuss it more quickly. Okay, so let's finish for today. So let's.
Можно повторить, что вы вначале говорили про почту, что вам писать?
Просто напишите мне, мало ли, вдруг будут какие-то, самый крайний, что отменится лекции или что-нибудь там, какой-то материал. Если просто вы мне напишите письмо, что вот я хожу на, то какие-то